Good afternoon, ladies and gentlemen. My name is Chiravachradej. Today we'll be discussing on a specific kind of a structure which is quite different from what we have done so far. So far we have looked at the general idea of structures, or in fact the more continuous material, usually signified by the word what we call rigid jointed frame or rigid jointed structure. The idea is that there is no discontinuum per se inside the structure. Well, there is certain change of the continuum, but there is no breaking of material, or the joint or the part of material can carry from axial force to shear force to bending moment. All kind of forces can be connected and can be transferred through the joint and through the section of material. On this structure here, which we call pin jointed truss, the mechanism or the load transfer will be a little bit different than what we have done so far. But we will leave that to the middle of the lecture, well, when we prove the theory and how we solve it later. Let's see the pin joint truss for today. What we talk about then, we'll talk about what does it look like, the pin joint truss, okay, and the definition of it. How do we define pin joint truss or not a pin joint truss, or any part of the structure that can be defined pin joint truss, the definition on and the specific characteristic of the structure to be called pin jointed. Then we'll discuss on the internal forces that transfer the load from member to one member to another until it reaches, of course, to the supports. Then with the internal forces in mind, then we will actually develop the way that how, or we discuss in fact, how we're going to analyze the internal forces of the trusses. Then of course, we will end with the example on the calculation, of course. Well, let's look at the pin jointed structures first. Usually the pin jointed truss uses for a very long span structure, for example bridges. Okay, you see that the one on the top that has the frame, on the top there you have the column, you have the slab going, and that on the top there is what we call the pin jointed truss. This is I think it's a pan put, I think. Never mind. This is another view of the bridge. Notice the framework from the floor. In fact, the beam or the floor hang on to that steel structure, which we call pin joint truss, not the other way around. Not the pin joint is actually supported by the beam. In fact, the pin joint truss support the structure, but the pin joint truss then transfer all the slab load and the beam load down to the columns. Okay, or sometimes this is a roof of factory. Okay, this is also on the top there. You see the truss going around. Okay, now the connection has to be kind of specific. The connection of the pin joint is like that usually. You see that joint. Okay, is actually signified with the word pin, meaning actually when we calculate it, when we analyze it, or theoretically, we think that the joint are pin, meaning it can rotate around. Well, it doesn't rotate because of other constraint, but in itself, the pin doesn't stop any. The pin in itself doesn't stop any member from rotating around the pin joint. Okay, so this is connection. The way we try to make sure that at the connection between the members, it becomes the pin joint, meaning it can rotate around. Okay, and that one is the idea, meaning all the forces from the members will meet at one point. Basically, when we look at the pin joint, we are looking at only the particle, or in fact it's a very small size, because all the forces meet at one point. Okay. Then definition then, if we have a truss, what is the specific characteristic that we call it pin joint truss? Okay, the first rule said that all connection must be pin type, right? The connection between a member has to be pin joints, the connection to the support. It could be pin support on the left hand side or the roller support on the right hand side. The word pin type meaning it doesn't stop rotation. Okay? Therefore, it cannot be fixed support, okay, by the way, because fixed support is not a pin type. This doesn't stop rotation, this doesn't stop rotation. Okay? So that's the first rule, is that the connection must be all pin type. Okay? Then all the forces must act on the joints, like that. Okay? That's okay. Not on the member. Now, you may argue, and rightly so, that the structure itself have a weight. The member itself have a weight. So, nevertheless, whatever you do, there will be some forces. At least the member weight will go down on the member, not at the joint. It transfers to the joint, but through the member, right? Which is true actually. But this is when we calculate, we have to make sure that the weight of the structure is lighter, very light compared to the weight it has to carry. So if that is true, if the weight of structure is so small compared to the total weight it carries, then we can ignore, or we can say that it has minimal effect, meaning very little effect, so we can ignore it. Not specifically theoretically correct, but in practical it is good enough. Okay? And one other thing is that after design we will have the safety factor to make sure that this kind of thing that we make assumption is covered, not by the calculation, but by the factor of safety. Okay? So, but anyway, so the weight of the structure itself must be quite light. So we won't see, we will not see this kind of structure in reinforced concrete. The weight of structure is too heavy. It tends to be in steel. The material will be steel, which is quite light compared to the weight it can carry. Okay? Now, so if that is okay, then let's go on. Usually, if it has the same span, or in this case, for example, they have 4 meters, all span is 4 meters. Sometimes rather than 6 times, they use the symbol at the bottom. 6 span at 4 meters, okay? Meaning it has 6 span, each span is 4 meters. It only works if each span are equal, okay? So that is, we are talking about the symbolic now, on how we draw it now, okay? The definition, the rules are that the two of them. One, all connections must be pin type, and all force. Number 2, all forces must act on joints. Okay, those are the 2 specific rules. Okay, next, because we have so many joints, okay, we have to find a way to separate the joints so that we know which one we're talking about. Well, usually it's used some kind of numbering system. Okay, the word numbering doesn't have to be numbers though. It can be ABC too. It can be กอไก่ ขอไข่ ขอควาย It's just as long as it's in a series of something that you can count. Okay? Well, or in fact you can give it any names you want, but be in a series of counting would be, well, most understandable to most people. Anyway, so usually just to make sure that, because we also have many members as well, so we have to find a way to separate the numbering between the joint and the member, because they are 2 different things. I tend to use either circle for the joints or maybe just a number like that. Okay? In this case, it means that joint 1, 2, 3, 4, 5, 6, 7. In one structure, we usually use one system. Okay? If we use circle for the joint, then it should be all circle. If we use only number without no circle, then everything is no circle for the joint. Okay? It should be same system. Now, what about the members? There are so many members and there are so many systems. Okay? Of course, we can use numbering, we'll discuss later, but sometimes a lot of people like to use the name of the joints to name the members. For example, each member has 2 joints, right? The beginning joint and the end joint, right? For example, if the member is having joint 1 and joint 2, then in some system they call it member 1, 2. Okay, meaning it's the member that has a joint 1 and joint 2. The other example is that 4 and 5, that member, therefore it is called member 4, 5. Okay? Or we can use numbering system, of course. I usually use the numbering system. Okay? In this case, I will separate the joint and the members using the rectangle, the box. Okay, either rectangle or square. The square or rectangle box in my system, it means members. In a circle or just a number, it means joints. But they are, well, different systems, and people might develop some other things too. I repeat myself, the word numbering doesn't only mean 1, 2, 3, 4. It also means anything in series. In this case, I also can do A, B, C, D. Okay? Okay. Once we got that, then let's talk about the internal force then. Okay? This internal force is something strange from others. Okay? Let's pick up one member and look at it. Any member, it could be any member. Okay? Just node I and node J. Right? One member has two nodes, right? Or two joints, joint I and joint J. This is a pin joint. We already know that a pin joint has been able to resist two forces 90 degrees to one another, no moment. So if we look at it, then when it contacts with the environment, emphasize on the word that the rule said that there is no force acting on the member. All forces must acting at the joint, right? So therefore, between I and J, there is no force. The only force it takes is the force taking from the joint. Now, taking from the joint, then the connection is the joint. Therefore, there are only two forces. With equilibrium, of course, then we have that one. Okay. Now, notice that RIX and RIY can be combined. It's acting on the same point. So we can just combine them. The same as RJX and RJY. So I can represent it this way instead. Okay? Fi come from RIX and RIY combined as a vector, not just plus, just as a vector. Same as Fj come from RJY combined with RJX. Now, if we have that free body diagram, then if we take moment about point J, the one below. Of course, let's say the length between I and J is any length L. So the moment about point J, Fj times 0, because Fj goes through the point, there is no 90 degree distance, Fj doesn't make any moment. So Fj times 0 disappear. It's only Fi then. But it's not Fi times L. It has to be the component that is 90 degrees to the length. In this case, it is Fi sine theta times L. But because there is only one force left in that picture, meaning Fj times 0 is only Fi sine theta times L, and it must be equal to 0. Now, specifically thinking is this: Fi is the force acting between the members. It should not be 0. It can be 0, but it's not always 0. So we cannot assume it's 0 for this general proof. Therefore, it must not be 0 for general proof. L is the length of the member. L cannot be 0 because if L is 0, then there is no length, there is no member. We are talking about a member, not a non-member, right? So L must not be 0. In that equation, if Fi is not 0, L is not 0. There is only one possibility then. That is, sine theta must be 0. If sine theta must be 0, then it means that theta is either 0 degree or 180 degree. 0 degree in this drawing, 0 degree will be tension being pulled apart. 180 degree turn all the way around, become compression. Nevertheless, then we can draw it this way, because we already know that theta is 0. So we draw it with the right theta, then Fi and Fj become on the same line, but because equilibrium dictates that sigma F must be summation of all forces must be 0, meaning Fi and Fj must equal to one another in this case, so I just call it F. Now, if we have that picture, then we can look at the internal force as the usual way we look at. Basically, we don't cut at a specific point. We cut at somewhere between the member, the 2 points, I and J. So in this case, let's say cut it at the distance x from point I. Then, there we are. Now, because we haven't proved anything yet, so I withdraw everything. F is already proved that it should be either 0 or 180 degree. Then we cut at the distance x. We don't know anything yet. Therefore, in this one, in 2D. Therefore, there must be 3 internal forces happening appear here. The axial force N, the shear force V, the bending moment Bm. Now I run out of space, so I'm gonna get rid of them. Okay, I put it up there. Then there we are. If we look at summation of the force in the direction of V, this line, okay, this line. Therefore, well, summation of any forces must be 0. In any line must be 0. But in this case, on that line, there is only one force, which is the shear itself, V itself, because F is 90 degree to the shear. F and N is 90 degree to the shear. Therefore, we can deduct that shear must be 0. Don't forget, this one here is a general proof. It doesn't specific on a member. Therefore, if we prove anything here, it must always be true. Therefore, it means that in the pin joint truss, shear doesn't exist. But, let me finish this first before the word but. Next then, if I take moment about point A, not point I, point A. Point A is where I cut. Now, if we look at that, then the shear force is at the point, therefore is times 0. It disappears. F and N is on the same line and go through point A. Therefore, there is no 90 degree distance either. So in that case, there is only one moment left, which is the bending moment itself. Therefore, bending moment must be 0. If we look at sigma summation of the force in the line of axial force, then this time is not 0 though. We have F, we have N. Meaning it doesn't have to be 0, but F must be equal to N. Therefore, axial force is not 0. The specific word should be N is not always 0. Shear is always 0. Bending moment is always 0. Axial force may not be 0. But this can only be true if the two laws apply. 1. All connection must be pin joint. 2. Or pin type. 2. All forces must act on the joint only and none at the member. And if that is true, only axial force exists. But that is the definition of pin joint truss. Therefore, this proof is for all pin jointed trusses. And there will be only axial force in it. Now, let's look at the way we analyze it. Okay. Taking advantage of the joint that has no moment is only the forces. They can reduce this into majorly two particle equilibrium. Basically, in this case, they will look at the equilibrium of the joints and how that we see. Well, just to be, well, so they name it. They name it method of joints, or sometimes called joint analysis. Or they could actually cut a section out and analyze section as the body, meaning we have 3 equations again. Okay, and that one here is called method of section or section analysis. In practical, you don't actually have to separate the two, meaning you can mix and match. But at this time, we just see example, just to make sure that we know both methods. Okay. Now let's look at the first truss. This is the first truss we look at. Okay. The joint is 1 on the top left, then 2 top right, 3, 4. Okay. The member has the square box on it. And we have 5 members here. The question line tend to be find all member forces or find all internal forces. It's not really specific telling you how many forces it wants. It's up to us to know how many forces we have to answer. In this case, we have 5 members. We already proved that there is only axial force inside a member. Therefore, there will be 5 axial force or 5 member forces to be answered here. The first one, let's try the equilibrium of joints or method of joints. There will be some other ways to go around this, but to me, the easiest way, and with the luxury of being able to check it, is starting off finding all reaction first. So there we are. In this case, then we will find all reaction by just normal general drawing of the free body diagram, right? The whole body and all the forces. Point 3, pin joint, not pin joint, sorry, the pin support. So two reactions. At point 4, there is one roller support, then one reaction, just usual. Okay. Then of course, sigma moment about point 3, we should get R4Y. Then sigma moment about point 4, then we should have R3Y. Don't forget that R3X goes through point 4, so R3X also times 0. And finally, sigma Fx to find out what is R3X. Move on. Okay. Now, once we know all the external forces, then we look, the word method of joint or the word joint analysis actually gives you a clue on what we're going to do next. Basically, we'll start to look at the joint. There will be some specific consideration of which joint we should start. It's not a fixed rule, but it is the rule that makes it easier. Well, we know that we're going to look at the joint analysis or the joint equilibrium. A joint is just a point. Basically, there's no size, so we're talking about particle equilibrium here. Then we have only sigma Fx and sigma Fy equal to 0 that we can use to calculate. We also have sigma moment, but because all forces pass through at that joint, therefore it always equal to 0. The equation gives you 0 equal to 0 all time. So it doesn't actually being used. It's only sigma Fx and sigma Fy for joint analysis. Now, if we have two equations, then we should look at the joint. We have two unknowns, not three. For example, point 1, 3-member contact. Therefore, there will be 3 internal forces of 3 members, 3 axial forces attached to that point 1. So 3 unknowns, because we don't know any yet. So that is not the point to start. In this case, I will start from joint 3. Notice that joint 3 has only member 1 and member 4 contact. Reactions we already calculate, so we know. So we have only point 1 and point 4, member force 1 and member force 4 to be calculated. Okay, if I draw joint 3, of course, the reactions we already know, 480 and 360. Then the internal forces, N1. N1 is, of course, axial force must be on the same line as the member, so N1 is definitely vertical. Since there is nothing else vertical apart from 360, and 360 going down, for equilibrium to be happen, N1 then must go up. If it go up, in this case, we know that it is actually tension. Same with N4. Okay, N4 is the only force left in the horizontal line. 480 going to the left hand side, the only way equilibrium can happen is that N4 must be going to your right hand side, which means then it's again tension. If we calculate positive, then it's really tension. If we calculate negative, then it becomes compression, of course. Okay, sigma Fx, then we get N4, and then sigma Fy, we get N1. Now, since we know N1, we know N4, so point 1 now doesn't have 3 unknowns. Point 4 doesn't have 3 unknowns. Okay, now at joint 1, there is only N4, N2, and N3 we don't know, because we already know N1. On joint 4, we only know N4, so there is only N3 and N5 that we don't know. Joint 2 unknown as well, so at this point, then we can choose anything, any joint to continue. Okay, update the picture so we know what we are doing. We have N1 and N4. I'm just writing it down on the truss so that the next joint we don't have to turn the page all the time. So let's look at joint 4 then. Joint 4, we have one reaction, 600. So just draw it. N4 we already know, we calculated last time, and I noted it down already. Tension going to the left. Now we have 2 more members to go. The first member I will draw here is N3. Now because N3 is in this line and N5 is in that line, so I know that N3 must resist the N4. N4 try to push it to the left hand side, therefore N3 must go to the right hand side. Now how do I add N5? Well, I'm not sure, I'm just guessing then. Okay. Oh, and N3, because it's going to the joint, it is compression. We assume compression, but well, don't worry about it. If it's wrong, when we calculate positive, it's compression. We calculate negative, it becomes tension. N5, we don't know yet because 600 going up, N3 going down in terms of vertical going down. So it depends on which one is bigger. I'm guessing 600 is bigger than N3, so I will assume that N5 coming down. If so, then N5 is assumed compression as well. When we look at this picture then, sigma Fy, we have 2 unknowns. Maybe not a point to start. Maybe sigma Fx first would be nice. There we are. If we do sigma Fx, then we can calculate N3 immediately. Then from that information, we can actually do sigma Fy. And apparently, it turned out that, I guess correctly, N5 is coming down, so we calculate positive. If it's positive, then it means that N5, well, the force coming down, which means N5 is in compression. There we are. Now, next then, we have done joint 3, we have done joint 4. Then, well, we can go update it. Now we have only one unknown left. Well, we can choose any joint. Let's go joint 2 then. Okay, joint 2. Then we have already calculated force. The top 240 is from the top 240 is from the apply, and then the bottom 240 is from N5, which we already calculate compression. Then we have 480 applied forces. Then N2, well, since there is only 2 forces horizontally, 480 going to your right hand side, N2 should go to your left hand side. If it go that way, it is tension. So the picture is drawn this way. Then sigma Fx, of course, will give you immediately N2 positive, therefore tension again. Now we haven't done sigma Fy yet. In fact, we haven't done joint 1 at all. Okay. Usually the equation left, you should have 3 equations left before you finish the calculation, and we're going to use that 3 equations to check the loop, whether it's really correct or not. So in this case, sigma Fy, then I have 240 minus 240, then it's equal to 0, which means sigma Fy is 0 equal to 0, which is good, so it's okay. If it's not 0, then you are in trouble. Meaning we have to go out and check where the mistake happens. Then that is 240. Then move on to joint 1. Now we know everything. Again, these 2 equations is for checking. Okay. In exam you don't have to check. There is no mark for checking. But if you don't check and you make a mistake, you take the consequences because you can check, but you didn't. Okay, there we are. Sigma Fx, apparently if you calculate it, we'll end up with 0 equal to 0. Sigma Fy, 0 equal to 0. Okay, again, if you did not calculate, don't bother to write it. There is no mark for it. So if you check, you check. If you don't, well, just write it without checking doesn't help anyway. So there's no point. So the summary is this, N1 to N5. So that is the joint method. Next then, this is a bigger truss, and this time I will do the section method. This is the specific way why we use the section method. usually when we design the truss, we choose sections and calculate the maximum forces inside those sections and then design every member according to that calculation. So because it's the way we order steel. The more cross section you have, the more member size you have, the more cut and throw away you do. Too much waste. Usually, if you actually design a part of the whole truss, the same cross section, using of course the maximum size that you need, is actually quite big. Most of the time save more money. So in this case, we're going to do the same thing here. So rather than calculate everything, maybe we just need just 3 of them. In this case, let's say we need member A, B, and C. Okay, with the forces. Now imagine the joint method first, shall we? The joint method, you probably need at least one equation to find out the reaction at the roller support. And then you have to calculate that joint, and then you have to go through at least 1, 2, 3, 4 joints. So in end, you need about 9 equations to get to A, B, and C. Those member A, B, and C. So maybe if we look at the section method, it could be easier. The first step, as usual, find reaction first. But in this case, if we design beforehand, then because each section we cut, we only have 3 equations. Then when we cut, we don't cut through more than 3 members. So if we look at this picture, then when we want to find ABC, we just cut through ABC, correct? Which means when you cut through A, B, and C, you can look at the left-hand side picture or the right-hand side picture. It's up to you. To me, in this one, once you cut it, look at the right-hand side picture will be easier because there is only one force to be contend with. Whereas you cut it and you look at the left-hand side, you have 400, R1X, R1Y, 800, and 800, or 5 forces to be calculated. It's a bit too long. Well, at least it's longer. So I'm going to calculate R2Y and then use that information, cut through ABC, look at the right-hand side picture, and then calculate the forces, the member forces straight away. There we are. Sigma moment about 0.1, then of course we can calculate R2Y. Once we get R2Y, then we move on, and then, as I said, cut and look at the right-hand side picture. Notice R1X, R1Y doesn't get involved here. Okay, and this picture have less forces. Once we cut it, then of course this is the line of the axial force. Now, this is the way how we look at the forces. If I want to know any line of forces, I find a point where I take moment and then consider which way the force go. The first one here, I look at NB. Oh, sorry, NB is not for the moment though. NB is easier to look because NA and NC is horizontal. In this case, NB is inclined angle. Now, there is only one other force that actually in vertical, which is the reaction. So if the reaction go up 700, there is only one axial force that can resist that force, which is the NB. Therefore, NB has to go down. If NB go down that way, then NB is a tension. Now, if I look at joint 3 then, basically if I take moment at joint 3, not really take a moment, thinking about taking moment, then NA times 0, NB times 0 doesn't count. It's only NC that make moment and the 700. 700 push up, making it rotate anti-clockwise, right? So to stop the rotation anti-clockwise, then NC has to go that way to create clockwise against it. Therefore, NC will go that way to your left-hand side. If it go to the left-hand side, then it must be tension. Now we have left with point A. Sorry, not point A. NA, axial force of member A. Now we're going to look at the point where we can take moment and eliminate NB and NC, the unknown. Right? In this case, that is where it cut. At the point it cut, I will call it point 4. If I take moment about point, don't worry about this. Remember the proof of the moment. If it's in equilibrium, everything is kind of coupled. You can take moment anywhere. Okay, it still have the same thing. The summation of moment on that body about that point must be 0. So if I take moment at what point 4, NB times 0, NC times 0. The only two forces that make moment is the reaction. Reaction point 4 is here, reaction push up here, create anti-clockwise moment. Now, this is point 4 and A is here to create the moment and the clockwise moment resisting the reaction moment. Therefore, it has to go from here to your left hand side and making this rotation. So it go to your left hand side. There we are. If it go to your left hand side, then it must be compression. That angle was given, 45 was given with the problem. So once we have the 3 unknowns, we can mark the lengths. And of course, we have 3 equations. We have 3 unknowns. We can solve them all. Sigma Fy, notice that however I think about creating the direction, the equation will follow, because then I can eliminate other unknowns. In this case, sigma Fy first for NB, then we can find NB, of course. There's only one unknown in sigma Fy. Then taking moment about point 3, then we get NC. Then taking moment about point 4, then we get NA. Notice that we haven't used sigma Fx yet, so we can use sigma Fx to check it up. And apparently, once we do it, it worked out to be 0. Sigma Fx is actually 0, which means 0 equal to 0. We have a good to go answers. There we are. So that is summary of the answers. In this case, we only need 3 answers because it asks for 3 member forces. NA, axial force in member A, axial force in member B, and axial force in member C. And that concludes the pin joint truss analysis. Thank you very much.